Hi, today we are going to talk about the tangent space to a level surface. This is my fifth attempt to record it. Yesterday I tried many times. I had problem with the audio quality. Let us see whether it works out fine. So what I am going to do is something I have not done earlier. Okay, namely I am going to use the PDF file which I was writing. Okay, you can see many times I marked it. I will use it now. Let us see whether it works. So let U be an open set in R3. Let F from U to R be a smooth function. Smooth meaning C to C infinity, whatever it is. Without loss of generality, we will assume 0 is in the image. That is, there is an x in U, so that fx equal to C. C is 0. Then the level set S is by definition F inverse of 0. That is set of all x in U, so that fx equal to 0. Okay, why is it called a level set? Okay, it is called a level set of F at level C equal to 0. An example is, typical example is F from R3 to R, F of x, y, z equal to Z. So, right, therefore F inverse of C is nothing other than the plane Z equal to C. Therefore, think of this as the plane. This plane is parallel to the xy axis and at level or height to C. C positive height or C negative. Okay, so that is why it's called a level. Okay, to get important examples of surfaces, we have to put an extra condition on S, namely for each A in S, since F is differentiable, I can talk about this gradient. Okay, the gradient, look at this gradient should be non-zero. That should be true for each and every A. This is a geometric reason why this condition is imposed. Okay, that is, we want to find at each surface, okay, at a point A, I want to find a tangent plane. If I find a tangent plane, there should be a normal. You will later find out the gradient F at A is a normal to the tangent plane. Okay, so I want to look at the tangent space. Therefore, what is our tangent space? Remember that I have to look for curves gamma from minus epsilon to plus epsilon to R3, so, okay, so that gamma of 0 is A, right? And gamma of course must be C infinity, smooth, C1 smooth or something. So gamma prime 0 is called the tangent vector to S at the point A, that is gamma 0. Okay, the collection of all such tangent vectors is what we call TAI of S. Okay, so gamma prime 0, call it B. So we want to understand B. Okay, so how do I do that? Let us look at, see, this is gamma going to T, but remember gamma T lies completely on the surface, right? Therefore when I compose it with F is 0 on the surface, therefore F of the gamma T will be 0 all the time. C, but C is 0 here. Therefore my function G, which is F composite gamma, that is 0 for all T here. Therefore the derivative of this constant function must be 0. But what is the derivative? The derivative is G prime T is gradient of F at gamma T into gamma prime T. Okay, because it's a composite of two functions, T going to gamma T and gamma T going to F of gamma T. Therefore the derivative of this is given by dot product with the gradient. The derivative of this at the point 1 is gamma prime T as a vector. Therefore the dot product of these two will be the G prime T, which must be a number. Okay, and you just like that take it for granted, or if you really want to understand, watch my calculus of several variables video, especially after chain rule. This is one of the important examples I will talk about. Okay, come back. Now what is I want to look at? I want to look at gamma prime 0, that is B. I want to understand that. Let's go back here. That means if I look at G prime 0, it is del gradient of F at A that gamma prime 0, that is B. That means my tangent vector B is orthogonal to the gradient. Okay, stop for a minute. What have you shown? Whenever B is a tangent vector to S at the point A, then B must be perpendicular to the gradient of F at A. Therefore, for all tangent vectors, will be a perpendicular to gradient of F at A, and that is why we think of it as a normal. Right? Now, one knows that TA of S is a vector subspace. Okay, and that therefore it is contained in the vector subspace, namely the orthogonal complement of gradient of F at A. By assumption, gradient of F at A is non-zero vector in R3, therefore its orthogonal complement will be of dimension 2. This will be of dimension 2. right? Therefore, TIFS will be a vector subspace of this orthogonal complement, and therefore this dimension will be at most 2. But we claim its dimension is 2. Why? That is where the implicit function theorem says. Implicit function theorem says the following. I am thinking of like R2, make a simple example. Okay, this is my U and this is my F inverse of 0, this is my A, the point A is here, right? Then implicit function theorem, what it says is under stated condition, I have an open set V in R2, okay, not RR, R2, and a function G from V to R, okay, this is not to here, G should be to R, okay, this picture is wrong, okay, so that, look at this, yes, intersection V, okay, V is something in R3, neighborhood of A, and intersect S, then this is the part of S is what I got, this is the curly lines, that is part of S, surface around A, okay, this is a relative neighborhood, open neighborhood of A in S, okay, so that is nothing other than the graph of this function G from V1 in R2 to R, okay, it's a graph of G, okay, but we had already found out the graph of G, okay, is dimension 2, okay, the tangent space to the graph of G is dimension in the earlier shots, right, and since locally, okay, the level set is a graph, this is a locally, this is a level set, this level set is the graph of G, but the tangent space to graph of G is dimension 2, therefore the dimension of the tangent space at A to S must also be dimension 2, right? Therefore, what we have is TAFS is a two-dimensional vector subspace of this two-dimensional space, that is orthogonal complement of gradient of F at A. Therefore, equality holds. So, what have we shown? TAFS is nothing other than gradient of F at A, perpendicular orthogonal complement. Okay. Now, to look at a typical example of this thing, let us look at F from R3 to R, where F of x, that is x, y, z, is x squared plus y squared plus z squared minus 1. Then F inverse of 0 is what is called unit sphere, x squared plus y squared plus z squared equal to 1, that is the unit sphere. Okay, this is the unit sphere, this is your point A, this point is A, and this is the tangent plane at A, right, that is point of contact, right, intuitively, that's what we think of, alright. We know, at least in coordinate geometry, etc., you must have seen this is perpendicular to the position vector. A is called the position vector, it is perpendicular to the position vector, right. So now V is perpendicular to A because the gradient of this function is 2A, therefore V is perpendicular to A, right. Now how do I get a tangent plane? We had already seen, to get a tangent plane what should I do? This is the tangent plane, the pink one, TIS, and translate it by A, then you get a tangent plane. Both are parallel and the common normal is gradient of F at A, which is 2A, and hence A. Okay, these are okay. I hope it made sense to you. Okay, and it was perhaps faster. This is what happens with the PPTs. Okay, if you write, it gives you time for you to think, because it takes time for me to write, right? Now it is already ready made. I just want to read it and say it. Okay, just for fun, let us test something. If it is agreeable to you, I will try to do the similar thing in future, but then possibly I will try to print. Okay, type it rather than write with hand. Okay, stay tuned, we will meet again.